Thank you very much for the invitation. I'm very aware that it's only me between you and the coffee and maybe some well-needed oxygen. So I'll try to make it brief, but bear with me. I think there might be hopefully some interesting insights in the study which I'm going to present. I see here the old slides, but here they are my ones. So, okay. So what I'm going to present is basically a summary of what's called the FVV fuel study. It's a study which Frontier has been commissioned to do the lead consultant job on, but it has been a huge exercise with, I think, more than 3 years and over 70 experts which has been involved. So it's really a collective effort which has provided these results. So let me take the next. The study has been published. It has been published in 2 parts. The first part already almost 2 years ago. I would say that's maybe the more boring part if you have the choice. That's where all the data is in and all the raw parameters. And then the results which I'm going to present right now has been published by the end of last year, and we have been working on this since then. No QR code here, but I assume the slides will be shared, so afterwards you can have the links on there. So what was the study about? It's basically determining the optimal technology mix to bring CO2 emissions in road transport down to 0 in Europe. Europe here, EU 27 plus UK. So basically we look into options for providing road transport in the projected amount based on 100% renewable. And if I say renewable here in the study, it's meant by PV and wind only. So biofuels haven't been part of the study, they might be part of the follow-up study. But in this study we looked at these 5 + 1, 7 different fuel pathways, which was electrification with different sources for the electricity, hydrogen in combustion engine, as well as fuel electric vehicles. We looked at Fischer-Tropsch based e-fuels, we looked at methane, we looked at methanol, and then we also used various combinations of it, particularly in the plug-in hybrid electric vehicles. We calculate these for 11 different types of vehicles, so for passenger cars, LCV, so we try to be as granular as possible. And building on the presentation which you just have received, we did this on an LCA based. So we not only looked at the vehicles and the fuel, but we always had the ambition to provide analysis on the full fuel supply chain. So as you can see here, that's an exemplary for the supply chain we modeled for battery electric vehicles. It really starts with the wind and the solar, and it goes through the transportation net, interim storage, distribution grid, wall boxes, etc. And you have similar pictures for Fischer-Tropsch, for methanol, for all these kind of things. So we really try to be comprehensive here and have all of these elements of the infrastructure also with all the relevant data. So cost, but also more important, CO2 footprint for building it. And then we calculate different scenarios. 11 what we call like single technology scenarios. I'm going to present them in a minute. That's basically, we focus on one single technology, assuming, okay, if we would like to defossilize road transport only using this technology, what would be the effect? So more like kind of academic question, because obviously in real it will be a mix, where we then also looked into, in the second phase, we looked at what's the optimal mix of technology, and then also we did several sensitivities, and I think since the study has been published, there has been additional done, so this is an ongoing process. So that's the aim, and basically in order to do this, and I'm not going into detail here, is we have built this Move It model, which is basically an integrated model which models the vehicle side and the transport and the mobility side at the same time as the fuel infrastructure. So basically it provides the links. Okay, if you assume that penetration of electric vehicle, that penetration of hydrogen trucks, for example, what does it mean in terms of required energy infrastructure? And that's the basis for all the calculation which I'm gonna show you. When you think about rolling out new technologies, you have to take care about the bottlenecks which you face, because obviously you cannot just flip a finger and then everything is there, but you have to roll it out. And we already learned today a lot about potential bottlenecks and constraints. And that was exactly one of the big task in this study to try to be as realistic as possible. What are the technical bottlenecks when we want to roll out specific technologies? And there were basically two big categories of it. One is this question of raw material, and we've heard about this morning already. So we also try to take into account for these different technologies, what are the critical raw materials you need? Platinum, copper, etc. And we have done the German Resource Agency involved to provide us what's the potential, what's the global potential and what's the European fair share which the European transport sector can claim from these resources going forward. And so we try to really be very specific here. So that's the one category, it's basically the raw material, and the other one is the infrastructure. So we already also learned about you need electrolyzers, you need battery production capacities, you need power grids, etc. All of these infrastructure has to be built. So we really asked a group of, I think it was over 50 experts from 77 groups across all the industries, what's basically the maximum speed you can, for your sector, assume in order to provide new infrastructure. And we called it the COVID-19 vaccine approach. So basically the logic is, usually when the development of a vaccine takes 10 years. But once the world agreed, okay, we now really need one in order to tackle COVID-19, it only took 1 year. So we basically asked all the experts, okay, if you take away all the financing problems, all the regulatory crap, all the problems with getting a permission, etc., just from a pure engineering and technology perspective, what is the maximum speed you could think of? How fast could you educate people to become installer, etc.? And there are just three charts shown here. We have similar graphs for all kinds of infrastructure, and you can see typically this is a constraint in the next 10 to 20 years. With enough time, you can do everything in this world, but it takes time, and therefore these ramp up graphs of the capacity provide particular constraint in the first one. So what we have done is basically take all these bottlenecks and incorporate them in our model, and then looked at these various technology scenarios which I showed you. And not going to present this in detail, but just to give you an idea, in every single technology you find bottlenecks which constrain the rollout in the various periods. And what's shown here in the rows are basically the different technologies, electrification, e-fuels, etc. And then in the three columns, what are the main bottlenecks in the next 10 years, in the next then 20 to 20 years, and 2040 to 2049. And you can see all technologies face significant bottlenecks in the near future, and some even in the long-term future. And if you take these bottlenecks into account and then try to see, okay, what's the maximum rollout which is possible for each individual technology, you end up with this diagram. It basically shows you the share of carbon neutral final energy demand in road transport, which will be provided by 100% renewable sources from wind and solar. And what you can see are the different colors are the different technologies, and then you can see the development over time. And what you can see from these pictures is, first of all, only the pathways which include e-fuels are capable of achieving 100% defossilization until 2050. That is particular because backwards compatible e-fuels don't have to wait for the fleet to change, because basically you can just use them immediately. Once they're available, you can use them in the existing fleet. All other technologies, you have basically the infrastructure and the fleet has to go hand in hand. And if there is a constraint, for example, on rolling out new battery vehicles, that put a constraint on electrification overall. It's the same for hydrogen, etc. So where we go for e-fuels, and this includes methane and also hydrogen, they allow for 100% switch until 2050 as a single technology. As we said, like we are very, it's a very academic question here. What can a single technology provide? Not all single technology will reach 100%. That has two reasons. One is because just the technology we assumed has its limitations. So for example, we didn't model methanol to gasoline in trucks because there you would need a diesel compliant, and therefore this MTG pathway can per definition only reach 60%, which is the share of fuel of non-heavy duty sector. But there are others, for example electrification, where you really have bottlenecks in the supply chain, and we will come to this in a minute, and therefore until 2050, even under this very optimistic COVID-19 vaccine scenario from a technology point of view, these bottlenecks prevent from reaching 100% if we only would have this technology available. What we then did is, okay, if we not look at one individual technology, but we combine them, and we basically started an optimization algorithm, a model which tried to select the combination of technology which provided the lowest overall CO2 footprint. So it's not in terms of cost optimization, it's a pure CO2 optimization. We want to be as low carbon as possible, aggregated over time. Then that's the fastest scenario which the model could create by combining different scenarios. And there's a very positive message in here. First of all, a mix of technology is always better than focusing on one single technology. And if we, under this very abstract and theoretical assumption from a pure engineering point of view, climate neutrality can still be achieved until 2039. It's no way it's going to happen, because we will, in practice, you will have to talk about finance and permits, etc. But from a pure engineering perspective, there are still ways to achieve carbon neutrality by 39 if you go for a mix of technology and try not to focus too much on one single technology. And this speed, to be able to be faster, this is the most important factor when you look at overall CO2 carbon footprint. Basically here again you see all these different technology graphs, but what is plotted here is basically the aggregated CO2 emissions over time. And what you can see is in the first 10 years, even close to 15 years, it doesn't really matter what you do. All the pathways up here are determined by mostly the emissions which remain in the existing fleet before you have replaced large share of the fleet with 100% renewable options. And only then after 2032, 2035, there's really a differentiation. And you can see that these single technology scenarios will lead to higher overall CO2 emissions over time. And as said, since some of them don't even reach 100% renewable in 2050, they will further increase after 2050. The mixed scenario really provides the lowest overall footprint, and just to give you an idea of the magnitude here, it doesn't seem like this delta is 5 times the total emissions in Germany. So not only road sector, but whole of Germany. So this is really significant. And that's why it's so important to be fast, because every year you lose before you make a decision, you are on this trajectory here, and you're just basically increasing the aggregated CO2 footprint. And in this regard, I think sometimes the debate we are having, which is very much focused, okay, what is really the optimal technology, and could it be a little better to do this technology than the other, is really a luxury we don't have. And the model results really tell, like, just do something, and even if it's the second best or the third best, or it turns out to be the fourth best, it still has an advantage rather than wasting time having debates. One very clear message from the data. So how is this mixed scenario then, how does it look like? And this is basically the fleet, how it developed for LDVs, so passenger cars and small LCVs. And what you can see here is basically we have fossil, gasoline and diesel phase out until 2035, diesel then on 2039. And what is happening? When e-fuels become available, they take quite long to become available because they have higher lead times for the production side, but then they can immediately be used in the existing fleet. We have plug-in hybrids, which are used as an interim technology, which makes sense because in the short term and the midterm, you have constraints on the electricity pathway, you have constraints on the e-fuel pathways. So combining these technology provides additional options and can therefore help to accelerate the rollout of carbon neutral vehicles. But once you have done your homework and the infrastructure is in place, then the disadvantages really count more of the plug-in hybrids, and therefore they are then either substituted by pure e-fuel or pure electric vehicles. So it's a clear interim technology. Interestingly, the model chooses methane-based vehicles for the bulk of the new coming vehicles, which is basically, if you have to build new vehicles and you have to build a new infrastructure anyway, then the advantages of methane are quite high because it is low carbon, quite low carbon requirements. It is an existing off-the-shelf technology for the vehicles, so it has a lot of advantages, which in this model world then makes it the preferred choice. We all know in reality there are different factors as well. Interestingly, battery electric vehicles are the blue one on top, and they're even decreasing, and I come to this in a moment. And then we have also hydrogen and fuel cell electric vehicles, which have their share. So, but why are the electric vehicles, where are they going? And that's, can you see on the next slide? From an optimal perspective, the electrification is happening in the truck sector. I have to say, we assume that there's going to be a catering line system available across Europe for the really heavy-duty trucks, so it might look different without it. But the logic is, why is this the model showing? The model says we are constrained on battery electrification capacity quite some long time, and it also comes quite with a high CO2 rucksack. So the production of batteries has a lot of CO2, etc. So I will use this technology where it has the highest impact, and that's in vehicles which drive a lot. So basically here, and therefore this electrification is primarily used in the heavy-duty sector, because there you basically get the highest return on invest CO2-wise, because you have to invest CO2 to get the infrastructure and the batteries in the world. And if you use them in vehicles which run like 200, 500, 1 million kilometers, their lifetime, they have a much higher effect than if you use them in passenger cars who drive, what we learned, like 10 kilometers on average. Again, all of this has been tested in sensitivity, so we see methane also in the heavy duty, we see hydrogen, both as fuel cell, but particularly also in the combustion engine, and as said, the electrification with the assumption of the catenary lines. We also did various sensitivities if the catenary lines are not available, if the very large batteries are not available, then basically hydrogen is the next best thing, which is then replacing the electrification. We've also done, and I said that, a lot of sensitivities. I'm not going into detail here too much, but just to give you an example what this model is capable of doing. Here are shown various model runs, and on the x-axis, you see the differences in the greenhouse gas emissions compared to this optimized scenario, and on the y-axis you see the differences in costs. And you can see, for example, that all mixed scenarios, and we did various mixed scenarios with an ICE ban, without an ICE ban, etc. They basically all are quite close to the overall CO2 footprint, but they come at different costs. So for example, if you take this Fit for 55 ICE combustion engine ban, it doesn't really, it has a small penalty on the CO2 emissions, but particularly it makes everything just more expensive without any gains. Obviously, if you relieve some of the constraints, so if you, for example, do some scenarios where you would allow electric infrastructure to be built without any bottleneck, for example, you get some additional benefits, but again, also they are not massively different. So you always end up with the same message, a combination of technology is always better than a single individual technology. Well, therefore, to sum this up in one picture before I come to the conclusion, that's basically the summary of the optimized scenario of the final energy mix. And I think the one message here is really the future. If you really want to become carbon neutral and you want to be optimal, so you want to do this fast, then you have to go for a colorful mix of different technologies. And as you can see here, this holds true even for 2035, where e-fuels and H2 make up for over 75% of final energy consumption, so the molecules have a strong role in this, electrification as well. But even if you then look at the end of the scenario 2050, even there, molecules still have an important role on top of electrification and the mix of the various technologies. That's really where the main savings come from. So, to sum it up, what can we take away? First of all, speed is of essence. So, we really should understand that everything we can do, even if it might not turn out in the end to be the optimal pathway, has an advantage compared of waiting for a decision on what the best technology is. Particularly the infrastructure and the material bottlenecks are a constraint and will be a constraint, and they are technical nature. They're not something which you can overcome by pouring money on it. It's really by terms of engineering capacity. So therefore, the only way to overcome them is to have different infrastructures in parallel and work on them in parallel, rather than to wait for one single critical bottleneck to be overcome. Without e-fuels, you cannot reach greenhouse gas neutrality by 2050. And if you go without e-fuels, you will see additional overall accumulated emissions. Mix of technology, as I said, is the best way forward because it can speed up the transition and therefore bears the lowest overall CO2 emissions. Drop-in capable e-fuels have a specific feature, which is they are compatible to the existing fleet. They take quite long to be developed and to be rolled out and to be available in large amount, but once they are available, you can use them immediately in all the vehicles. While for all the others, you have to wait for the vehicle and the infrastructure, and all this has to go hand in hand, which overall slows down the deployment. The good news is, ideal regulatory and financial conditions, we can still reach greenhouse gas neutrality, but the bad news again is, this would require an amount of infrastructure which I think would be to a degree which we haven't seen ever in Europe, and therefore I think we should really start a debate how much of these are we really having the right framework in place in the EU to facilitate this technology open approach where different technology can as quickly as possible ramp up in order to contribute to an overall low CO2 footprint. And just one final word, because that is often asked, banning combustion engine vehicles does not help. It's just an additional constraint, and everybody who has done modeling, like an additional constraint can only make the outcome worse, can never improve the result. So that's also what we see here. Banning ICE vehicles would lead to higher greenhouse gas emission and higher cost than necessary. Thank you very much. Now it's coffee time.